after the cycle.
You have two circles, circle C1 and circle C2. Then you have a common tangent, so a tangent that passes through both these points, and these points are labeled as P and Q. Right, so that's M, and you're supposed to show that Pn bisects Pm. Oh wait, that's one.
No, MQ bisects.
Oh yeah, there was a typo.
Oh yeah, MQ bisects PMR. Yeah, that's okay. Sure. So when you read this question, it just begs for tan chord somehow, because you have a lot of tangents and just random chords in a circle. So guessing some of you probably thought of tan chord or some way to use it. So there's a bit of another construction. So you add these lines in that, and there's another one. Okay, sure, and that. So then we're trying to show that an PMR bisects this. There was another code. Oh yeah, that's that. Okay. So now you know that by tan chord, that's equal to that, right? By tan chord, and that should be equal to this, because that's the tangent, and this, let's call this, okay. And that should equal to that, right? But because RMNQ is cyclic, this is also equal to this. RMNQ is cyclic, so that angle is equal to that angle. And the sum of these two angles is equal to that, because that's the exterior angle of a triangle. So that plus that is equal to this, so this is equal to this, and therefore that bisects that. So that's just one.
Oh my gosh, that is true.
I mean, you guys will get detailed solutions to try and process it properly, but that's just me going over it really quickly. So for today's lecture, so we're doing so if you can recall, yesterday we did the in center and the in circle. So that's when you take the angle bisectors of each of the angles, and the point where they meet is called the in center. And it turns out that that's the center of the circle that's inscribed. And the X center is very similar, just that we take a point that's the external angle bisectors, meaning the bisectors of the angles which are just outside the triangle. So if we have the triangle ABC, and we take the bisectors of these angles, so the exterior angle of ABC would be this angle here, not the internal one, and that there. So it turns out that if we take the angle bisector of these, meaning this is equal to that, and that's equal to that, then we should have meet at a point such that this is the center of a circle that touches each of these sides. So there's a circle that touches each of these sides. And this circle is called the AX circle. So it's called the AX circle. And its center, denoted by IA, is is the x, the ax center. So very similar to the in-center constructed by angle bisectors. And to show that this circle actually exists, we consider the two angle bisectors of external angles of ABC and ACB, and they meet at some point here. You drop a perpendicular from there, and a perpendicular from here to there, and this side as well, same thing. And to show that that's equal to that, to show that this is actually a circle, it's just this side is common, that's the same, and that's a right angle. So these two triangles are congruent, so that's equal to that, and similarly that's equal to that. And since that's 90 degrees, these are tangents, and they lie in a circle. They lie in a circle with center IA. So that's how you construct the x circle and find the x centers. Everyone with me? And then, which will lead me to a very important lemma, or well, maybe not that important, but very useful lemma. So a lemma is kind of like a theorem, but it's not a formal theorem. So maybe if it's well known, you can just state it's a lemma, but if not, you usually have to prove it. So lemmas are like tools that you use for solving different problems, which are not necessarily theorems, so you can't just state them as they are and assume everyone knows it. So the one that I'll be doing will be the in-center So in the in-center x-center lemma, we begin with a triangle ABC. ABC. And we let I be its in-center. So I is just its in-center, and then if we reflect the point I, sorry, and then consider its circumcircle. And then we let AI meet the circle again at L. And if we reflect I across this point, meaning we construct a point such that IL and IA lie on the same line, and IL is equal to LIA. Then we have that IAB bisects the external angle of ABC, and IAC bisects the external angle of ICB, meaning that's equal to that, and that's equal to that, and therefore being the x-center opposite A. Does everyone understand? understand that. So that's equal. Yeah, that's true. So it's at
Saying from the x-end to the 2 points on the triangle, those are bisectors of those angles.
yeah, those are bisectors of these two angles. So that's what the problem statement says. The lemma says. I is the circumcenter. No, I is the incenter.
Oh.
Constructed by yeah.
Oh, the circle.
So yeah. So it's like putting everything together. Consider the circumcircle and the incenter. So it's not just the not just the circumcenter and the circumcircle. Yeah.
But then how did they get those lines at the bottom?
Which lines?
The IA.
Oh, IA is okay. IL is a point where IA meets the circumcircle of ABC again, and IA is the reflection of I across L. So meaning that it's a point such that IL is equal to LA, and IL and IA lie on a straight line.
Oh.
So that's what a reflection of about a point means.
So that IA has nothing to do with the IA above.
Yeah, it's just a name we give it because we know what the point is. Well, after you prove, you know what the point is, and so we just choose to give it this name because we know that it's the X. Yeah, it's the X center, AX center. Okay, sure. And now we move on to the radical. Axis. So the power of a point, as you can remember, is we take P, could be inside or outside the circle, and we construct a chord to the circle that intersects the circle at A and B. And the power of the point P was defined to be PA multiplied by PB. Right? And we showed that no matter where we choose A and B, it's fixed. So if we were to choose A, say A prime here, and B prime here, then that's still equal. So, and yeah, we show that that's equal, and regardless of where you choose A and B, and this is called the power of point P, this product, which is denoted by power of point B, power of point P with respect to the circle. So if you give the circle a name, say gamma, so power of a point P is equal to this product. But then these 2 points, such as A and B, are just random points on the circle. So that doesn't really tell us much of what this constant is. So we have to choose a specific A and B such that this is nicer to work with. So in other words, choosing a spatial chord of the circle, and if you can recall some of the spatial chords, well, probably the only spatial chord in the circle will be the diameter. So we consider point points x and y such that xy is the diameter of the circle gamma. So gamma, right? So this will give us a nice expression for this after we actually calculate it. So since xy is a diameter, the center lies halfway between x and y. So call the radius of the circle r. And call the center O. So xo is r, and oy is also r. Right. So now power over point P is equal to the product Px multiplied by Py. And so and Px is equal to Po minus r, because that's r, that's Po, so Po minus r. So Po minus r, and Py is equal to Po plus r. Therefore, if you expand this, we get that the power of point P with respect to the circle gamma is Po squared minus r squared. So yeah, that's useful. And another way we could have done this is consider a point where consider a point z. Consider point z where pz is tangent to the circle. So if you draw in a line OZ, then that's perpendicular to pz will be perpendicular to OZ, since OZ is the radius and PO is a tangent. And so by Pythagoras we know that PO squared is equal to OZ squared plus PZ squared. Right? And by definition of power of a point at a tangent point, that was just PZ squared. So, and the OZ is equal to R. So PO squared minus R squared is equal to PZ squared, which, since that's a tangent, is equal to the power of the point P with respect to gamma. Now moving on to the radical axis. Does anyone actually know what the radical axis is, or has anyone actually seen it before? Okay, probably some of you have. So now we know these different points P where the power of a point is some constant or some number that you know about P. So now we're saying if we have two different circles, when is the power of a point P with respect to both circles actually the same? So that's what we mean by the radical axis. It's the set of points. So you should write this down. It's the set of points P such that the power of point P with respect to gamma 1 is equal to the power of point P with respect to gamma 2. So that would be the radical axis of circles gamma 1 and gamma 2. Right? So you have two circles, they could intersect, they could touch. One could be inside the other, but you'll just choose a random one and say they intersect. So it's a set of points. It turns out that it's a line through where they cut for the case when they intersect. So yeah, so each point here would have the same powerful point with respect to gamma 1 and gamma 2. And we will show that this is actually true, actually holds regardless of the circles. So yeah. So we consider two circles. Okay, now I'll just make them. Call them C1 and C2 this time. C1 and C2, right? And this is when actually coordinates are actually better than using synthetic geometry. So it's, by synthetic I mean just angle chasing and different lengths and stuff. But using coordinate geometry, or some of you might notice analytical geometry, is actually better in this case. So you denote by this, by O1 the center of C1 and O2 the center of C2, right? And we assign coordinates to these 2 points. So O1 is given the coordinates A and 0, and O2 is given the coordinates B and 0. So we're just placing this on the Cartesian plane. So that's just the x-axis where, because the coordinate of that is 0, the coordinate of that is also, the y coordinate is 0, and that's also 0. So we're trying to find all points P, call them P, and give them coordinates x, y, such that the power of point of P with respect to C1 and the power of point P with respect to C2 is the same. So we notice that by that definition, the power of point with respect to C1 is equal to O1 P squared minus so is equal to O1 P squared minus R1 squared, and power of the point P with respect to C2 is O2 P squared minus R2 squared. Right? By that definition over there of the power of point. Now OP squared, finding the distance between two points on the Cartesian coordinate plane, is just the same as subtracting the x coordinates. So OP squared would be x minus a squared and plus y minus 0 squared, since the y coordinates of O1 is 0. And that one over there becomes x minus b squared plus y minus 0 squared is equal to R2 squared. That's minus R2 squared. And both of them are equal to, this is equal to the power of point C1 and this is the power of point C2 for any P which has coordinates x and y. So now, since we want these two to be equal, we equate these two. So then x minus 2 minus a squared plus y squared minus r squared is equal to x minus b squared plus y squared minus r2 squared. Right? And then doing a bit of algebra, this cancels with that. And on the left hand side, we get that. The left hand side, we get that x squared minus 2ax plus a squared minus r1 squared is equal to x squared minus 2bx plus b squared minus r2 squared. So the x squared cancel from this side and this side, and take everything to one side. So we have negative 2ax plus 2bx plus a squared minus b squared minus r1 squared plus r2 squared is 0. And taking x as a common factor here, we have x times negative 2a plus 2b plus a squared minus b squared minus r1 squared plus r2 squared is 0. Now we have the equation of a line where this is some constant, because a and b are just constant depending on where the circle is, and AB are also constant here, and r1 and r2 are just the radii of those circles, and that's also constant. So we have a linear equation. So if you take this as some constant alpha, so you have x alpha plus, and then take this as beta is equal to 0. So that's an equation of a straight line. So therefore, these points actually do lie in a straight line. And it turns out that it's actually a straight line such that is perpendicular to both these. So the radical axis of two circles would be a straight line which is perpendicular to the line between the two centers. So that's something very useful to know and often. Any questions?
Why is it 2y and not y2?
X the coordinates.
Which one?
P is 2y and not y2, but the others all a0 and b0.
P is?
It takes 2y.
Oh no, P is xy.
Oh,
So we don't know anything about P, so we just give it random coordinates. So we're trying to find where P must actually lie so that it satisfies both equations.
The radical axis is always perpendicular to the line joining.
Yeah. And if they do intersect, it's the line that's joining. It's the line that's joining their points of intersection.
So you could have used that in today's problem.
I don't think you could have. There's no problem for it.
No, I was saying the radical axis.
Yeah, there was a radical axis, but it doesn't really give anything because you're not chasing the ratios, you're chasing the angles between them. So radical axis is mostly for ratios because it really doesn't give anything about angles. It gives products of lengths, and from products of lengths you can get ratios of different lengths. So yeah. Okay, before I move on, I'll probably add something as a side note. There's something called the South Pole theorem. So it's called the South Pole theorem because a couple of years ago there was students who were here at Stellenbosch and who were attending the camp, and they were just playing around with some geometry stuff, and they ended up founding a relation, and they named that after them. It's not official though, even though in South African Olympics we can use it because everyone knows it and we recognize it, but it's not well known. Well, it is well known, but it's not really a theorem around the world. But it is something that I find pretty cool, that students who are just at a camp can end up finding an interesting result and make it their own theorem, if you may say. So I'll just quickly state what it says and prove it because it's not that bad. It states that if we have a circle, the circumcircle of triangle ABC, and we consider the angle bisector of BAC and the perpendicular bisector of BC, it states that these two lines actually meet on the circle. So if you take the angle bisector here and the perpendicular bisector of BC, then these two lines meet on the circle. It's not hard to see because if you construct, call the point where they meet x, so not assuming that it's already on the circle, call it x. Now B, x, and CX subtend the same angle, therefore they're equal. So you say that's equal to that, right? And since that's equal to that, and that's equal to that, and that's 90 degrees, oh, that's common, and therefore, well, assume that that's equal to that, that's equal to that, therefore, oh no, wait, no, what am I doing? Okay, so we haven't assumed that they're on the circle yet, right? So,
I don't see X. So that's where it's supposed to land.
so now, since that's the perpendicular bisector of that, so that's common, that's 90 degrees, and these two are equal. Therefore, that's equal to that, because these two triangles are congruent. And that's equal to that, since those two triangles are congruent. And since they're also congruent, that means that that's equal to that. But then these two angles subtend the same angle, therefore these have to line the circle. Because that's equal to that and they subtend the same circle, so that has to. So that's. And probably another important theorem, which is called the. Let me see if I can write it here. The angle bisector theorem. So if we have a triangle ABC and we have a point, so ABC, and we have the angle bisector of BAC intersecting the circle at D, and the angle bisector theorem states that the ratio AB divided by BD is equal to AC divided by CT. So if and only if that's an angle bisector. And to prove this, we use some trig. Maybe some of you, or most of you, might know a bit of trig. And yeah, you can maybe try this. Any ideas on how to prove this? Okay, Rashid. Okay, no idea. So we use the sine law of triangles. Maybe some of you might have heard of it, so I was a bit skeptical on not doing this because some of you might not know it. So we know that BD divided by sine alpha is equal to AB divided by sine theta, right? Because we're considering this triangle here and using the sine law on it. So for those of you who don't know the sine law, it's the sine of the angle over the opposite side is proportional across all the sides. So BD here, BD over sine A will be AB over sine theta. And on this triangle, we have CD over sine alpha is AD divided by sine 180 minus theta. And since sine 180 minus theta is just the same as sine theta, so that's just AD divided by sine theta. So here we get that the ratio BD over AB is equal to sine alpha over sine theta. And from here we also get that CD divided by AC is equal to sine alpha over sine theta. And so these two ratios are the same, and which is just the same as like by taking the inverses. So that's called the angle bisector theorem. Pretty useful as well.
In line 2, is that AD meant to be AC?
Choose?
In line 2. Over, is that meant to be AC or
Yeah, AC. Sorry. Yeah.
Sorry, line 1 there, shouldn't that BC be a BD?
Line 1 should be?
BC at the end, just before that last one, BC, should that be BD, right?
Sorry. Okay, now moving back to the radical axis of more than two circles. So now, since we already found the power of a point for one circle and a radical axis for two circles, you ask yourself what happens when we have more than two circles. Is it a line? Is it another set of points? Is it a point? What is it? Yeah?
For 3 circles, I think it's a point.
Yeah, it's a point. And does that point always exist?
Yeah. For 3 circles, yeah.
Does it? And for two circles?
For 2 circles,
Does it always exist for two circles?
yeah.
Okay, so he says it exists, and I claim that it doesn't. So maybe you find yourself bored in this class. Probably try to find two circles such that the radical axis of those two circles doesn't exist. Because it actually does. It's not always true that it exists. So now the condition that the radical axis for a point such that the power of a point P for all these three circles exists is the condition that these three circles should intersect. So if they don't intersect, it's not necessarily true that they have a radical, we call this a radical center in this case because it's only one point P, such that the intersection of, the line through the intersection of these two circles, and these two circles meets at a point, just at a particular point called the radical center. So the radical that's the definition of the radical center. Should I do this? Yeah.
So I just want to make sure, in that figure, is there 3 radical centers?
So no. So this is the radical. So this is the radical axis of these two circles because it's the line that's connecting the points where they intersect. This is the line that's connecting these two, and these two.
Didn't you add another line in
Yeah.
there?
Okay, well, I drew this kind of. That's supposed to be a point here. So you have this, and that, right? So these two circles intersect there and there, and draw a line here. These two circles intersect there and there, and here, and these two intersect here and here. So yeah, that's how it should have looked like. So the point where all these intersect is the radical center. So if like that. Fair enough. Cool. Oh yeah, I also want you to demo a problem that I found out. So we have an acute angled triangle, and H is its orthocenter, and prove that the reflection of H about the line BC lies on the circumcircle of triangle ABC. So as you can see, there's two different triangle centers here. So often in questions you'll find different centers where you have to connect them because they are largely connected. Especially the orthocenter and the circumcenter, they have special properties together, and this is one of the properties that it might be useful to know as a lemma, even though it's not a theorem itself, but I still find this pretty useful. So we'll try to solve this problem. So that's its orthocenter H. So what we're trying to prove here is that the reflection of H about this line is the point here, which we do not know yet that it lies on the circumcircle. Let's call it point T, and we're trying to show, and such that that's also equal to that. We're trying to show that that T lies on the circumcircle of ABC, meaning that A, B, T, C is cyclic. So we have to show this. RTP stands for required to prove that that's actually true. So, any ideas? Since this is not really a theorem or anything, it's actually a problem and could easily be in a test or something. So, any ideas? What would you try to do first, or what do you notice first? Yeah.
Maybe construct BP and PC.
Yeah, that's a good idea because then you can try to find similar or congruent triangles. Well, not similar in this case, congruent triangles only. Yeah, and there's like 2 steps after this and then it's solved. So this statement is equivalent to saying that triangle T, let's call that point X, TXC is congruent to triangle HXC. Because if that's true, then that's equal to that, and that's equal to that. So therefore, that's cyclic, and which is what we wanted to prove. Right? So if we can manage to show this, which is, I think, obviously true by looking at the diagram, that shows that this is cyclic because we know that this angle here is equal to this angle here because triangle, because quadrilateral ADFC is cyclic because that's 90 and that's 90, so they subtend the same angle. So that's equal to this here because of the cyclic condition. And this is obviously congruent to this because that's equal to this by construction. That's 90 degrees and that's common. So that's equal to this. But then since this is equal to this and this equal to that, then these two are equal, and therefore BTCA is cyclic.
Wait, no, it's just the first cyclic chord you pointed out.
So ADFC cyclic. So okay, I'll remove it from here. So we have AC here, we have that, and something like that. So that's 90 degrees and that's 90 degrees, right? So if you consider this as a chord of a quadrilateral, then it's both of them subtend 90 degrees. So therefore that's cyclic.
Sorry, I just want to check, is X and X now the same point?
Yeah. Yeah. So that's cyclic, and therefore that's equal to that. You see why that's cyclic, and that's congruent to that, so that's equal to that. So then, if you reflect the orthocenter about one of the sides, then that point lies on the circle, which I find really cool. And similarly, that would be equal to the point here, call this y, and that would be equal to the point z, so that's equal to that.
So did you assume that TXC was congruent to HA?
Well, I didn't assume it, because what we do is we reflect. So we don't know anything about the circle yet.
You don't know-
We reflect we reflect h about AC.
Okay.
So then hx is equal to xt, and that's common, and that's 90 degrees. So that's congruent. And as an exercise, you can try to prove it when ABC is not acute. So it also holds. So if you have an obtuse angle, one of them, so the circumcenter lies outside the circle, and the orthocenter also lies outside. It's the same kind of work, because you're just chasing cyclic quads and congruent triangles, but it's slightly different, not that different. Oh yeah, and this triangle that's formed by connecting the feet of the perpendicular. So feet of the perpendiculars refers to if you drop a perpendicular from A to BC, and that point where BC intersects AX, well, that point where the perpendicular intersects BC is called X. So that's the foot of the perpendicular from A onto BC, and E would be the foot of the perpendicular from B onto AC. And the triangle formed by that is called the orthopedic triangle. So in this case, DXE. And as an exercise, I'll leave you to prove that this triangle, the orthopedic triangle of ABC, so DXE, is similar to triangle ZTY. So that's an exercise that I'll leave for you. You can use what you just did now, like from there it follows easily, but yeah, so you can just try to prove that.
So I'm just a little bit lost. Why did we now say that ABXC is cyclic? I understand it is a cyclic triangle, a cyclic quad, but how does that help you to in the end say that point T lies on the second circle of ABC?
Okay, so ADXC is cyclic, right?
Yeah, no, it is cyclic. I agree
and-
with you with that.
And therefore that's equal to that. So DAX is equal to DCX. So
Oh.
that's equal to that. And from that's also equal to that because of congruent triangles, so that's also cyclic.
Yeah, right. Just needed to know that. Yeah. Because then you can say that that angle at A is equal to the angle at C because BT is suspended both and therefore T must be equal to
And I do have time, so I can quickly do this as well. So once we've gotten this result, this other result is follows very quickly. So we have to show that this triangle TYZ is similar to this small triangle XED, right? So from here we know that HX is equal to XT and HE is equal to EY because we just proved that there. So therefore, by the midpoint theorem, that's parallel to that. And similarly, that's parallel to that, and the last two lines are also parallel, right? So therefore, this angle here is equal to this angle here, right? And no, not that angle big. This angle here. And by the midpoint theorem on ZHY, that angle here is equal to this angle here. So that angle is equal to this small angle. So we get that DEH is equal to angle ZYT. So similarly, we do that for all these angles, and we get that that angle here is equal to this one here, and this here is equal to this here. So these two triangles are similar.
Sorry, DEH or DEX? No, right?
DEH. It's DEH. So those two angles are actually equal. So yeah, I also find this pretty cool because it looks like you just constructed two random triangles and you just extended lines, but it turns out that these two lines are actually similar, and since they share a common center, we say they're homothetic. So meaning one of them is just fixing a point and then scaling it to a different size. That's what homothetic means. I find that pretty cool. Any questions? Anything unclear you'd like to for me to clarify? Or